Hi guys, sorry I'm not there today, so I'm going to try to do notes this way. You're going to look at some PowerPoint and I'll show you a couple of things just using the webcam. And this lesson isn't too bad. So last time we were talking about the sampling distributions and we talked about being able to find X bar. You'll see the answers for that homework are posted above this video, so you can check your answers there. Today we're going to be talking about the mean and the standard deviation of X bar. So the first thing here is the definition. The mean and standard deviation of the sampling distribution of X bar are called the mean and standard deviation of X bar, which sounds kind of silly, but yeah, it is kind of silly actually. But because we're calling it, instead of having to say the mean of the sampling distribution of X bar, we just call it the mean of X bar. And we'll know that they are denoted this way: mu sub X bar and sigma sub X bar, respectively. Now we have to consider that when we look at a sampling distribution, so I'm going to pull one up from our last class. We looked at this sampling distribution last time. And remember, this was from the 5 test scores. Here we go. There it was. There was the 5 test scores. And we said, hey, what happens when we choose only 3 test scores? Here are all the possible combinations of choosing 3 of those 5 and the mean of those samples. And so that's how we can calculate X bar. Now we're going to be finding the mean of the X bars. So really we're looking at the mean of the mean in a way. Now we can calculate the mean and the standard deviation in a couple of ways. I'm going to switch this over, I think. Yes. There's 2 ways that you can do that. The first way is to use the formulas. Here are the formulas, and I hope that they show up correctly for you. These are the formulas that help us calculate just the mean and the standard deviation of a set of numbers. Okay, so that's one way that we could do that. We would have to do some more calculations from that chart in order to calculate these, but we could still do it. The other way is that we can always use the graphing calculator to help us out. So let me remind you how to do that. I'm going to turn on my calculator here, and I'll help you kind of walk through this. So remember, you're going to go to the stat button. It's right here. So I'm going to push stat, and let's see if I can make that a little bit clearer. Let's see, this way, sorry. And we want to maybe edit a list. So I'll hit enter on edit, and you can see that I've already put all the X bar value. Okay, maybe, oh there, that's better. I've already put all the X bar values in there from that chart that I just showed you. So that's there. So once you have the values in there, I'm going to quit. I'm going to go back to stat. I'm going to arrow over to calculate, and we want to do one variable statistics because we're going to use just that one list of values. I think the sun is causing issues. There we go. And so we just hit enter a few times. And there we get the one variable statistics, and we can see that the mean of the X bars, or the mean of all the means of those samples, is 80.6 with a standard deviation of 3.3 down here where it says sigma X. Okay, that's the standard deviation. Okay, so there's a couple ways that we can find means and standard deviations. Let's go back here. And I'm going to go back to the next slide. And so what we're going to find, if it'll click, there we go, is that the mean of the sampling distribution of X bar is always equal to the mean of the population. So mu of X bar is equal to mu itself. So that seems kind of silly to say, but that's the way it works. Yeah. Because ultimately, when we look at a sampling distribution, we have included every possible scenario that could happen. And so every test score is represented the same number of times. And so, yeah, it kind of makes sense that they would be the same. Okay, so we have that, the mean of the means. The next thing we will talk about is the standard deviation of the sampling distribution. The standard deviation is represented this way. Sigma sub x bar is just the standard deviation of the population. That's what sigma is, divided by the square root of little n. Little n is the sample size. And then you'll notice also that it says this formula is used when little n divided by big N is less than or equal to 0.05, where n is the population. So we want to use this only when our sample is less than 5% of our population. So this formula actually gets used a lot when we're talking about very, very big population sizes and we're taking a small sample. If I'm talking about the average number of cars that every household in the United States owns, but I'm going to use a sample that is only drawn from, a few cities, then obviously our sample is very small compared to the population of households in the United States. So we could use this formula to find the standard deviation of that. However, if our sample size is not less than 5% of the population, then we have to use a different formula to calculate the standard deviation of x bar. And you can see there's a similar part of the formula, but then we have to have this, okay, where this square root of population minus sample size divided by population size minus 1 is called the finite population correction factor. So sometimes when we consider thinking about like an infinite population, we're having to kind of reduce it down to being a finite number so that we can actually do some work with it. Okay. Next, let me see what else. If there's anything else I wanted to say about that. I don't think so. I will just kind of a quick note. Let me see what that one says. A quick note about this is that for most practical applications, your sample size is going to be less than 5% of the population. So most of the time, this is the formula that gets used, just because when we're dealing with real world statistics and not just things like there's 5 people, then we're going to be using lots of bigger numbers. So, and you can consider even for a moment that if we really did have a population of only 5 test scores, why wouldn't we just calculate the regular mean and standard deviation? Why would we try to take a sample to estimate the mean or estimate the standard deviation? That seems kind of silly. So if we've got a small number in the population, we would just calculate mu and sigma. Otherwise, we're going to have to use x bar. So there it is. 2 observations regarding the sampling distribution of x bar. The spread of the sampling distribution of x bar is smaller than the spread of the corresponding population distribution. So keep in mind that when we're looking at the standard deviation of x bar, we're trying to find out how much the sample means differ from the actual mean, okay, versus with regular sigma of just x, we're trying to find out how, maybe in the case of our test scores, how far does each test score differ from the mean of the test scores. And so because x bar, when we have mu of x bar, we're talking about the mean of the means. Our standard deviation of the collection of means is going to be smaller, always. And it makes sense when you're thinking about the way that it gets calculated. Again, looking at the formula, we would take the population standard deviation and divide it by some number, where this is n is the sample size. You're probably not going to be dealing with a sample that has a size less than 1. So in every case, you'll be taking the standard deviation and dividing it by some number larger than 1, which is going to make, obviously, this number be smaller. So it makes sense when you think about it with the formula. And then secondly, the standard deviation of the sampling distribution of X bar decreases as the sample size increases. So that also sort of makes sense, because if I have 5,000 pieces of information and I say, hey, I'm just going to have a sample of like 20, and I'm going to find out X bar of those 20 samples, and then I'm also going, I'm going to, find X bar of just using these samples. When we find that standard deviation, obviously it's going to be a little bit not as close to the actual mean as it was before. Whereas if I have 5,000 pieces of data and I choose a sample size of 2,000 instead of a sample size of 20, I'm probably going to get a better estimation of the actual mean and the actual standard deviation, or how far away from it, the standard deviation that the mean is. Okay, so let's look at what you're going to be doing on your homework today. Here's an example. The mean wage for all 5,000 employees who work at a large company is $27.50 per hour, that would be. And the standard deviation is $3.70. Let X bar be the mean wage per hour for a random sample of certain employees selected from this company. Find the mean and the standard deviation of X bar for a sample size of, so the first one we're going to do, part A, of 30. So let's look at it here. N equals 5,000. Mu is 2750. Sigma is 370. In this case, we can see that 30 divided by 5,000 is indeed less than 0.05. So mu X bar is equal to, again, mu always. So that's 2750. That's not going to change. We can calculate then sigma X bar, which is going to be sigma, which is 370, divided by the square root of our sample size, which is 30. And we come up with $0.676. I would probably, because we're dealing with money, I would probably round that to 0.68. Okay. We do the same thing when we're talking about a sample size of 75. We could, again, can see that 75 out of 5,000 is still less than 5%. So our mean of X bar is still 2750. Again, that's not going to change. Our standard deviation then is calculated as 370 divided by the square root of 75, which again, I would probably round this to 2 decimals and call that 0.43. So you can see as the sample size increased from 30 to 75, sigma X bar decreased. Okay, that should always happen. That's how we know we have a consistent estimator. Okay, that it's going to be a good estimator. And then part C said find out what happens when we have a sample size of 200. So again, 200 out of 5,000, that is 0.04. So of course, less than 5% of the population. And we have mu X bar, which is still 2750. And we have sigma X bar, which will be our standard deviation divided by the square root of 200. Again, that population or the sample size went up, but sigma X bar went down. So that is what's going on. And that's the kind of stuff you're going to be looking at on your homework. And I'm, I think, ready to show you what that's going to be. So hopefully this makes sense. If you have any questions, try to read through the book. And if you have any lingering questions, we'll talk about it on Tuesday when I see you again. So here is the assignment. I'm going to hold that up for you on section 7.2 on page 283, numbers 11 through 16 all. So you'll do those problems. They're not too bad, pretty straightforward. Okay, so have a great weekend, and I will see you on Tuesday. Bye.